and you can see clear. Now that's what I want.
Okay.
So in this way, you will have a bigger view. Okay. So you will have a bigger view what's going on that monitor.
No problem.
Yeah. Okay. So hi, good morning, everyone. Can everybody hear us clearly? Good.
Yes. Yes.
Okay. So now let's start. So today we have James from Anton-Paar, and he's an expert to help us to connect our rheometer and our Raman. So he will give the demonstration and the presentation on how to use it. Thank you.
Right. Okay. So, yep. Thank you. So as my name is James Eichhoff, so I'm the senior product specialist for Anton-Paar USA. So I've been doing rheology for almost 2 decades now. I've been with the company about close to 15 years. So kind of to show you what the instrument can actually kind of do to you in this case. So you have the single-use setups that you can use the rheometer by itself for just characterizing viscoelastic behaviors, as well as the Raman for basically looking at the chemical structure. So by allowing that we can do something with the rheometer, which is using a different base plate, which is a glass plate that we can actually optically see through, and then we have this linear table down below that we can kind of then position itself, that allows us to do Raman and the rheology kind of in situ together, so we can kind of do both at the same time and collect data while we're running these measurements in this case. It's usually useful if you're it has a wide range of applications, mainly if you're kind of seeing a change in kind of a chemical structure, either from shear or even from a temperature change condition that you can kind of monitor these conditions. So things like shear-induced crystallization, if you're seeing phase changes, so think of kind of a palm oil fat where you melt it. It's very liquid-like, but as you kind of slowly start to cool it down, it crystallizes, so you would see kind of changes in the Raman peaks, or shifts in this case, that would kind of be related to kind of different structural changes. And you can kind of get that from the Raman, as well as the rheometer kind of, syncing the 2 sets of data together in this case. So that's kind of the setup in a nutshell. I mean, the main thing is with the rheometer, it is an air-bearing rheometer, so you kind of want to ensure that it has air at all times. You'll see on the front display of the instrument that should say status OK, and that indicates that you have enough air pressure that the bearing is floating in this case. From there, you can choose the measuring system that you want. You have 2 options in this case at the moment. You have a PP50. It's actually labeled on the cell as to what it is. And then when you actually install it, you'll see here is that you have what we call our Toolmaster chip. And that's what actually gets read in this case, so you don't have to kind of program anything into the software, tell it what it is. It simply connects. If you look at the quick connect collar, you simply raise that up. This goes through what we call as our Peltier hood. So you heard the beep, that indicates that inside there's an RFID antenna that reads off of that chip and then tells the software exactly what it is in this case. So there's no need to kind of go back into the software, say it's a PP50 or any other information to that. So it's already pre-programmed in there for the setup. So from that, I mean, then you can start into the software.
How about when you share it?
Oh, you want to share the screen?
Yeah.
All right. All right. And so I have simply just pull it out Rheo Compass. It's simply this this icon here to pull into the software that we go into. And then so from there, we simply just go into the software. It now detects, like I said here, it's PP50 with its geometry, also the measuring cell that you have. And then we can simply just click here to set the zero gap for the system. And so what it's going to do is it's going to kind of look for contact with that lower plate and zero off of that in this case. So basically, like I said, looks for 1 Newton of force, and then from there it backs off and readjusts back up to the gap in this case, which in this case is a 1 millimeter gap in this case. And so then from there, we're ready to set, basically to start a measurement. If that's just doing simple viscoelastic measurements without the need for Raman, or you could also do where you're doing these rheological tests with the Raman setup as well. In this case. So any questions on, or any application questions on kind of what to do with the rheometer or anything you're looking to do with the rheometer? Okay, so
Yeah, no question, I guess.
If there aren't any other questions, I guess we can then start to look into the actual Raman software in this case. So with the Raman software, it's kind of fairly straightforward per se. You simply open it up, and then you can kind of come in here into the settings. The wavelength for the laser that you're using for this is always going to be a 785 one. We don't have a high temperature fiber optic for the 1064. You can also then set here your exposure time. So if you don't want it to say auto expose, you want to set an actual time. You can simply unclick this and then set your time, which is always in milliseconds. You can also adjust the laser power level and then your scanning and time delay.
What's the range for the laser power we can tune?
I think 300 is the max, from what I remember.
300 is the max, okay.
If you set anything above the max, it will dampen away. You want to be kind of mindful of that, because if you're dealing with something, the more power you put into it, it could actually damage the sample, which is what you're not trying to do in this case. So you want to be mindful of that. And so the settings up here are all based on it being run kind of in a single point mode, which is basically you click to start, it collects the data at that single point, and then it gives you the spectrum. Below there's this what we call continuous spectrum acquisition. So if you put here where it says total scan count, so typically it's left at 0. So if you said for your application, I know I want to collect 20 scans. I can tell here 20, run that method, it will just run 20 scans. Now, if the measurement goes longer than that time frame, you won't have any additional data from the system or from the Raman to go. Then here at the bottom this is basically for delay time. Because the laser itself has to turn on and turn off, so we just allow this for a cooling time. Typically, it can be anywhere between 5 to 10 seconds, and so you can just always set it that way in this. Okay. So it's always something you can adjust and play around with. Okay. The thing to remember, though, is that the acquisition that the rheometer can collect is always going to be a lot faster than a Raman spectra can be acquired. Because you can see here currently, it takes 5 seconds for the exposure time for that. In that same time frame, the rheometer can actually collect, a point every 10th of a second in this case. So you'll have to kind of line up the timestamps, which is what the Raman already does, is when it saves a spectrum point, it gives a timestamp, which then you can kind of relay back to the rheometer in terms of the real time. And since they're both on the same computer, it's using the Windows account time, so you'll have the actual data set in this case, so it'll make it a lot simpler for you to go. And so once you're ready with that, you'd either save it as a method, that way then you can load it in the future if that's how you want to. That might be something I'd recommend, since this is a shared facility, is that people then, because every time this defaults back to its original settings, and this way you don't have to kind of relay back to that. You can always just click here to say save that method, and then load it at the end. Once you're ready to run, you would just come back to set, and then from there you can actually run to start the measurement. What I would recommend is, when you load your sample on, is to first click on what's called a single acquisition. In this case, that way you kind of get an initial baseline, and then click, say, here onto S2, and then when your measurement starts, is to just click on run method in this case. Because that way then you have kind of a baseline point of what the sample was like prior to starting the test. And then every time a new spectrum is acquired, it will kind of compare it back and forth to the first baseline point, so you kind of be able to see that going on. So,
could you briefly introduce the plate we just changed, because the hardware part is different from.
Right. Yeah. Yes. So I believe Norbert may have been here.
Now we focus on this.
Okay. So the plate you had previously was different. So it had a chrome oxide finish, so black finish. Instead, now we have this glass finish. And you can kind of see, if you look here, this is where the laser is at the moment. You have this black ring I'll fully take it apart. So this kind of opens up the whole system from underneath that you can kind of see. So you can see the laser is what it's held in place by is an adapter probe, and underneath that is basically this what we call a linear table. And what the linear table allows you to do is this micrometer allows you to move the laser. So if we look at the laser currently, so you can see how I can move. So if you have sample where the material changes, or is it homogeneous, you can actually do measurements or move this micrometer at different positions along the radius of the geometry in this case, depending on the nature of your material. Now, on the other side is another micrometer. So where this micrometer moves left to right, the micrometer here is ideally used to move up and down. So basically for positioning of the laser. Ideally, once you set the laser up as it's supposed to be, you don't need to reposition kind of or position the laser because it's in the optimal position for the focus length.
Mm-hmm.
The reasoning that micrometer is also there is because, again, this is an optical system, so it can be used for other things outside of Raman. It could be used if you're doing anything, say, with microscopy or small angle light scattering, or doing anything with kind of a curing setup that you have that flexibility to kind of focus into the system. And so the glass that comes with it has kind of a coating onto it. So you'll see, hopefully you can see, it says this side up, that's the way it's supposed to be positioned in. So it simply just goes in. This then gets screwed down. And then you basically just screw until you feel resistance, and then it's in place. Mm-hmm. And then you can kind of use the bubble level that came with the instrument to level itself again if it needs to be.
Okay.
Or if the instrument was moved around.
Okay.
Okay. So it's a relatively, I can actually show it if you want to see how easy it is. So you can do one of two things. So if you're not going to be doing high temperatures, because the cell as is currently can go up to 200 degrees C with the water bath that you have, and probably about as low as like -10, -20 degrees C. The only small thing you have to consider is that your sample is sitting on glass. Your Peltier elements sit around the glass. So there's going to be a heat distribution or a thermal gradient in the system. Now, if you're closer to room temperature, it's not going to be as big of an issue. But if you're going to really high temperatures, that's something that you'll have to consider. You can either calibrate the system with what we call a CSA wafer to take that into account, or swap it out in this case. Because as it is currently, you can leave it as is to just do all your standard measurements. But to take it out, it's relatively straightforward. Is this micrometer just removes off from the side that's over here. Sorry. So this just unscrews. Underneath, there are kind of two clamps that pull out the fiber optic probe. And then this whole piece just lifts out in this case. So you can probably, in the span of, say, 10 to 15 minutes, be swapped to the other setup that you had currently. Now, the nice thing also is because like I said, is you have the glass plate, is you have the flexibility that if you want to do something with like a polarized microscope, is on this linear tram, is you would just buy the microscope components, which would be the lens, the microscope tube, the camera, and then the light source in this case. And then a software update to let the video monitor feature in so that you can kind of connect the data, the visual data to the raw data points. So yeah, so that's another feature. Or additionally, you could also, in some cases, if you have your own microscope setup or tube setup, you could do that as well. Some people have done that to go with.
Okay. So let's move on.
Sure. So I guess what we can do is I can set up trying to run a measurement. So hopefully this works.
Okay, I want to introduce what I got.
Yeah. So I just have an antibiotic, so I think it has some type of it's basically like a somewhat grease-like. So hopefully, if I melt it, maybe we'll see some change in the formulation. Hopefully, that is the goal.
Yeah, we grab it from the first aid kit, and yeah.
so in the software, what we'll do. All right, so we'll just come down to a very narrow gap. So then it suggests to trim the sample, so then I can just move down a little bit further. And then we can lower the hood to kind of start the test if we want to in this case. So the first thing I would do is come over to the Raman software. So the nice thing with our setup is because you can see the hood is completely over the laser, so there's no way for someone to look underneath or look directly at the laser and go blind in this case, because it is a 3B laser, so you want to be very mindful of that in this case. And so then we can just click here to click on single acquisition. And so it waited 5 seconds because of the settings. I had left it at 5 seconds to do that. All right. And so now we have a spectrum in this case. And we can just come back to it. And if you actually want to remove it, we can just click here to clear all. And we'll start with S1 again. We'll just repeat the same thing.
So in S2, we already have that.
Yeah, I had set it as S2 initially. I wasn't thinking. So, I mean, it's not going to change much. So then now I can just click here on S2. So you could do a number of things. One is we could just do a stagnant test. For instance, then the software, I just want to go to, say, 40 degrees C. And then here I can just tell it to, say, run the method. This will just let it run continuously. So we're not doing anything in terms of rheological data. We're using the rheometer as a way of, say, collecting, controlling temperature, yeah, and then seeing what occurs in this case.
So it will only keep on updated.
It will only update. So it always.
I'll keep everyone, or I just got the last.
No, so it will keep everything. It just will.
Okay.
It's just gonna, because it's S2. It's always gonna replace the next measurement in this case.
But in database, I have already.
Correct.
Okay, that's good.
Yeah. So you'll see they're all individually in this case. So this might not be an ideal material, but I mean, you can kind of see this kind of function in this case. So what we can at least do is, but at least here in the rheometer. So if I look at the rheometer, so at 25 degrees C, there was a force on it. So that meant the sample was very rigid and it was pushing up on the system. So it was becoming it was basically solid. Now the force is gone in this case. There's nothing really on the system. And I can actually then just say, try something else. So now we can actually then tell it to kind of cool down in this case.
So I need to keep a record of how the time.
So the Raman isn't going to read the temperature from the rheometer. So I'm doing this kind of in a stagnant mode. So ideally, the best thing I would have done would have been to run a measurement. That way, at least I had the timestamp of the rheometer to the system, and then you can kind of correlate the data back and forth. So let me just click here and stop. Because now if we kind of come to, so now if you want to see the data, you can see all the spectrum in this case that will run. And then you kind of pull those out. And then, like I said, as you would monitor there, because if I go into the open spectrum, so 2021, 3, 5, time, minute, hour, minutes, seconds. And you just well, it's going to be just the time of whatever's on the computer. Yeah. So you would line this up because if we were to actually look in the software, so I'll pull up. We can just do is pull up. Is you can actually pull up additional data in the software. Where you can kind of say the time of day. And did you know what day you ran it on? You can see here. So this is always going to be in military time. So it will be. So for instance, if this was, it'd be 1626. So then you could kind of pinpoint that data to each other.
Okay, Ken, do you have any other question? No more questions.
No. Okay.
Where is the temperature sensor located?
So the temperature sensor, so you have the hood and the plate work together, but where the actual temperature is read is right here. So there's actually Peltier elements around that quartz glass plate, and so that's where the temperature is being read from. Ideally, we'd want to be as close to the sample as possible, but with the glass quartz plate, that's kind of, we don't have an easy way of doing that. So we're as close as we can get. And that's why I said, if you plan to do really large temperature ranges, it might be useful to get what we call like a CSA wafer or calibration probe that you can kind of stick underneath the plate and then do kind of a temperature range to where you set the temperature to be, say, 20 degrees or whatever the highest range you're going to probably be going through, and then calibrate it, because then you'll know, okay, well, the sample, for instance, if you did this and you probably went to 40 degrees C, likely on that plate, it might be around 39 degrees. So there's a 1 degree offset.
Yeah.
So what you could do is use that information with the CSA wafer, and it's actually it can actually be easily programmed in the system. So if you just click here to go to measuring set, start measuring set function, calibrate, you would put the wafer in, and then it would automatically do it for you. Set the temperature ranges you want, and then it just automatically would do that. And then afterwards, what it would do is, when you told it to go to 40, it would go to a sample temperature of 40. So likely in that case, like I said, if the sample was reading 39 and you the plate or element was at 40, it would actually go to, internally the instrument would be going to 41 degrees. Because the system temperature doesn't matter, it's the sample temperature that's most important. So this was what you would do in this case for that. So.
Thank you.
Okay. So I guess I got a question is do you have any plans or what you're looking to possibly do with the Raman and the rheometer together? As to kind of what type of samples you're doing. I mean, I know we've done I guess I can share with you some of the various applications we've done. Because I will give you some better idea. Because without kind of a sample, it makes it a little bit difficult to show the Raman. As you can kind of see here, is that we kind of just pulled something, but ideally in that case. So
I searched online and got a link. You hosted a webinar like 2 years ago about the application. Yeah.
Yes, me and the lead scientist for the Raman. I can send you that link as well, unless for the webinar as well as anything else.
Yeah, that'd be great.
So.
When I got a video, I will share with everyone. So make sure anyone needed to take a look. So James hosted a webinar like 2 years ago, talk about the applications.
Well, some of the early applications that we used with the Raman and the rheometer.
That's good.
So,
do we have any more questions or anything you'd like to take a look? What's the resolution? Raman.
What is its resolution? I might say it in the manual. It depends on the system. In terms of the kind of the wavelength numbers, it's about 6 to 9. This is what I think it's looking at.
Oh, that's the one.
Yeah. So when it's a 785, it's 6 to 9. When it's 1064, it's 12 to 17. That's the range in this case. I mean, it's also the manual. Oh yeah, yeah. It's in the instruction manual. That came with the instrument, so you can kind of use that for looking at.
Right. So we have the manual, have all those informations. Yeah. So the question is, you talked about the importance of selecting the laser power properly. Is the manual includes any information about that?
Yeah. So
how to choose the power?
Yeah. So if you look in the manual on the back on the technical specifications,
I think we are actually. Yeah, that's what. Okay. Now.
Okay. So you can see here. Basically, what the max should be between 0 and 450. So that's kind of where you want to be. Ideally, the higher the power, the better the intensity signals in terms of the wavelength numbers. But like I said, in some cases, your material might be damaged by it. So one thing you can always check is by either starting from a lower wavelength or a lower power and slowly increasing it. I've seen that in most cases for the 785 using 300 milliwatts is typically a good practice in this case. I mean, because the only higher it would be 450, so you're not much higher in this case for what you're doing.
Mm-hmm. Ola, could you unmute yourself and then ask a question?
Yes, I wanted to ask a simple question. Maybe I got distracted and missed the point. So your setup is working with polarized light? And if so, how do you control the polarization of light?
So with the polarized light, again, I can't do this without actually pulling something up. So you have a tube, so it has an analyzer and a polarizer to it. On one is where the inlet for the light source comes in from your system.
Mm-hmm.
And so basically, if they're parallel to each other, that allows the full light to come through the system and back to the camera. There's a simple little lever that just turns to give you kind of cross-polarization in this case. And then you'll see kind of the field go, or the image go dark unless there's some kind of orientation going on.
So in principle, you can control the direction of polarization of probing light with respect to, let's say, shear direction.
Correct.
And then if you're working with orientationally ordered samples, you can deduce things like the scalar order parameter.
You could do that. So if you're looking at scattering, you could do it with a laser, with like a laser coming down through, and then kind of scattering onto the. That's another way of doing it, because then you could do. Oh my God. There's different ways. There's HH, VV, and then VH and HV. So you have those full flexibility with the small angle light scattering system.
Yeah, great. Thank you.
No problem.
So it's, oh, me it's typing.
Okay.
Let's see. Okay. So yeah, I guess.
Oh, that's for the polarized imaging setup.
Oh, okay. Thank you, Thorsten. So I guess if no more question, we will end today's demonstration. And thank you, James.
You're welcome, no problem.
For others. And if you have any question, I will make sure I have his.
I'll make sure to leave a bunch of my business cards that way in case you have other questions going forward with that. And like I said, I'll also send you some information. I don't know if you needed information, either application or anything else related to other things like the polarized imaging, or I see you already have access to the website in this case.
Yeah, great. Okay, thank you all. Have a nice weekend.
Okay.
Okay, let me put this down. Yeah, everyone just wanted to thank you.